Alrighty guys, let's go ahead and get started with these rotational inertia notes. So some of you guys might be asking yourselves, what is rotational inertia? Well, rotational inertia, represented by the letter I, is a property of any object that experiences rotation. It is going to be a scalar, meaning that it only has magnitude. It does not have direction. And again, it is represented by the symbol I. It's going to tell us how difficult it is to change the rotational velocity of an object around a given rotational axis. We are familiar with linear inertia, which just told us how easy it was to speed up or slow down an object linearly. If you remember, an object that had more inertia was due to the fact that it had more mass. Rotational inertia, which is going to depend on its mass and radius. So the more inertia there is, the more momentum an object will have. And we'll talk about that later on the next few slides. But that makes sense because inertia depends on mass, and if we remember, momentum also depends on mass. The main difference here is that rotational inertia depends on mass and the radius of the object, where linear, just moving left to right or up or down, only depended on mass. Let's talk about point mass rotational inertia, because this is the one that we're going to be using most of the time. So point mass really just means that we are taking all of the mass of an object and we can sum all of that to be at one specific point. The equation is going to be I, which is rotational inertia, is equal to m times r squared. M is going to stand for the mass and r stands for the radius of that object. Again, the symbol is going to be I for rotational inertia, and the units are going to be kilograms times meters squared. We can see from this equation that as radius increases, so does the rotational inertia. So the bigger radius an object has, the more rotational inertia it will have. And we can also see that as mass increases, so does the rotational inertia. So the more mass an object has, the more rotational inertia. Again, the rotational inertia just tells us how easy or difficult it is to change the spin of an object. Object rotational inertia equation depends on their shape and hollowness. So if an object is solid, it's going to have a different rotational inertia than if the object were hollow. And you guys are going to hear me use rotational inertia and moment of inertia. They're the exact same thing. Let's talk about Newton's second law of rotation. So we should be a little familiar with this. We talked about net torque in our last notes, but we're going to talk about the equation here. Net torque is going to be equal to the moment of inertia times the angular acceleration, which is going to look something like this. We can use this equation to find the angular acceleration of a rotating mass, assuming we know its torque, mass, and radius. From this equation, we can see that as the angular acceleration increases, assuming the moment of inertia is staying the same, the net torque will also increase. And we can see that assuming the net torque remains the same, that as the moment of inertia decreases, the angular acceleration has to increase. Which makes sense because angular acceleration tells us how easy or difficult it is to change the spin of an object. The more moment of inertia we have, so the bigger that I value, the more difficult it's going to be to change the spin of that object. Meaning that the smaller the I, the easier it is to change the spin, which would give us a greater angular acceleration. Let's take a look at an example down here. We have a merry-go-round experiencing a torque of 100 Newton meters, and it has a rotational moment of inertia of 50 kilograms times meters squared. What is the angular acceleration? So this one should be pretty easy. We have our equation, net torque equals moment of inertia times angular acceleration. Plug in our net torque, which is 100. Plug in our moment of inertia, which is 50, and then multiply by the angular acceleration, which is unknown. Simplify and solve, and we find out that the angular acceleration in this specific case should be 2 radians per second squared. Let's take a look at this conceptually now. Let's say that we have a solid beam that can rotate without friction around its center 0 when forces are applied. So the center 0 just means here, 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 and here. Which combination of forces is going to cause the greatest angular acceleration? And we can assume that the beam is divided into 4 equal parts as shown. Well, in order to figure this out, we need to think about our net torque equation. Net torque is equal to I times alpha. So if we rearrange this to solve for the greatest angular acceleration, we're going to solve for alpha here. So alpha is going to be equal to net torque divided by moment of inertia. We can say that I is constant because all of these objects have the exact same shape and they're all rotating around the same axes. The biggest net torque then is going to give us the biggest angular acceleration in this case. So if we look at all these cases, we need to look for two forces that are basically working together. So over here, we see these two forces are working together, but we see that this is 2F and this is F, and it's not super far away. And we know that the biggest net torque is going to occur on the edge, so as far away from that pivot point as possible and the biggest force as possible. So this one's not going to be our answer. Next, if we look over here, we see that we have two forces, but they're pushing in opposite directions, meaning that they're working against each other. So this is not going to help us out either, so this isn't our answer. If we look here, we have two big forces, and they're both pushing in the same direction. I would argue that they're both pushing counterclockwise, so they're going to create some net torque, but they're not super far away from that pivot point, so this is also not going to create the biggest net torque. Therefore, our answer is going to be right here, where we have our two forces pushing in counterclockwise directions as far away from that pivot point as possible, giving us the biggest net torque, which is going to result in the biggest angular acceleration. I want to show you guys some common shapes that we might see for moment of inertia. So up here we have a hoop about a cylinder axis. And we've used this before in lab, but we might see this again later on. It's a very common shape that we use in physics. Its moment of inertia is mr squared. You do not need to memorize any of these, but I want to make sure that you guys see these and are used to them when they pop up. Next, we have a solid cylinder, and this moment of inertia is mr squared over 2. Next, we have another cylinder about a cylinder axis. This one's a little bit more rare, but this is when there are two different radii. So here we can see how that moment of inertia is. And then lastly, we have a thin spherical shell about any diameter. And this is the moment of inertia for a spherical shell. If you take a look really quick at all these shapes, you're going to see that the biggest moment of inertia is going to be produced by the hoop about a cylinder axis. And the smallest moment of inertia is going to be produced by a thin rod about an axis through the center. Again, the smaller the moment of inertia, the easier it is to move the object. The bigger the moment of inertia, the more difficult it is to move the object. Let's take a look at an example here. So we got our buddy Sean, and Sean has a solid ball and a hoop, and he wants to spin each around its axis of rotation. They have the same mass and radius. We want to find out which object is going to have more rotational inertia. Well, if we look at the rotation of inertia here, we can see the equation for the sphere, and we can see the equation for the hoop. The hoop's equation is mass times radius squared, where the sphere is 2/3 mass times radius squared. Therefore, the hoop is going to have a greater rotational inertia than the sphere. Another way of thinking about it is that the hoop's mass is distributed further from its center, and because the mass is further from its center, it's going to be more difficult to move. So now we want to figure out what can we use moment of inertia for. So moment of inertia can help us when we're solving for rotational kinetic energy. The equation is kinetic energy equals half times moment of inertia times omega squared. Again, that K stands for kinetic energy, I stands for moment of inertia, and omega stands for angular velocity. Another thing it can help us solve for is angular momentum. Angular momentum is going to be represented by the letter L, and we know that L is equal to I times omega, where again, L is the angular momentum, I is the moment of inertia, and omega is the angular velocity. All of these equations should seem very familiar because I is the rotational moment of inertia, where m, or mass, would be the linear moment of inertia. And if we converted all these to be linear, we would have 1/2 mv squared. And if we did the same for angular momentum, we would have P equals m times v. Something that's super important is that objects can change their shape and still conserve their angular momentum. So when we say angular momentum is always conserved, that's what we're talking about, and I'm going to show you a GIF in just a second to explain that further. Over here, we see this physicist on a chair spinning around with weights in his hands. As he has the weights outstretched, he moves slowly, but as he brings them inward, he moves faster and faster. The reason for that is that if we look up here, as he brings these weights in, his omega is getting bigger and bigger, where his moment of inertia is getting smaller and smaller. How do I know his moment of inertia is getting smaller? Well, moment of inertia depends on the radius, or where that mass is distributed. When he brings his arms in, he's shrinking that radius. And if he's shrinking that radius, he's shrinking his moment of inertia. Since angular momentum is conserved, that means that his angular velocity is increasing. Some of you should notice this from figure skating. When you watch the Olympics, you see them spin around, and when they want to spin really quickly, they bring their arms really close to their body, and when they want to slow down, they spread their arms out wide. Now let's look at a kinetic energy example. So rotational kinetic energy we talked about before is K equals 1/2 times I times omega squared. We have two hoops with the same mass and radius that are released from rest at the top of two identical ramps. One hoop rolls without slipping, and one slides down the ramp without friction. We want to figure out which object is going to reach the ground first. So this hoop that is rolling means that it is experiencing linear velocity because it's moving in a straight line, but it's also experiencing rotational velocity because it's rolling down the hill. The one that only slides is only experiencing linear velocity. Before the objects are released, they only have potential energy because they're both at the same height and they're not moving, so they would just have potential energy. The rolling object is going to have both translational and rotational kinetic energy because, like we said, the rolling object is moving linearly left to right, but it's also spinning around, meaning that it's moving rotationally. Where the sliding object is only sliding, which means that it's only experiencing translational, or in other words, linear kinetic energy. The sliding object doesn't have to convert the potential energy into two kinds of kinetic energy. Therefore, it will have a higher final linear velocity and reach the ground first. The rotating object has to transfer its potential energy into both translational and both rotational kinetic energy. Because of that, it's going to have a slower linear velocity when it reaches the bottom, and it's going to reach the bottom second because it's reaching the bottom at a slower speed. A good way to think about this is that the sliding object takes all of its potential energy and transfers it into kinetic, where the rolling object takes all of its potential energy but splits it up between its translational and rotational kinetic energy. Since its energy is split up, it is not going to have the same translational kinetic energy as the sliding object. It's going to have much less, and because it has much less translational kinetic energy, it's going to be moving slower at the bottom, meaning that it's going to take longer to reach the bottom than the sliding object. Now let's take a look at angular momentum. So again, we have our equation for angular momentum we talked about on the last few slides. We have a figure skater that can change her angular velocity omega by changing her arm position. When her arms are outstretched, she has an initial angular velocity of 0.67 revolutions per second. If she pulls her arms in tightly, she changes her moment of inertia. And she changes that from 4.6 to 1.2. Remember, a decrease or a smaller moment of inertia means that it is easier to spin. We want to calculate the skater's angular velocity in revolutions per second when her arms are pulled in tightly. So like we just said, her moment of inertia has gotten smaller, so we would expect our revolutions per second to increase when she pulls her arms in tightly. First thing we're going to need to do is remember that angular momentum is conserved. Therefore, the initial angular momentum should equal the final angular momentum. So we can set the initial equal to the final, and then we can go ahead and solve for our angular velocity final. So we get angular final velocity is equal to initial moment of inertia times initial angular velocity divided by my final moment of inertia. When I plug my numbers in, I get 4.6 times 0.67 divided by 1.2. Simplify and solve, and I find out that the angular final velocity when her arms are pulled in tightly should be 2.57 revolutions per second, which makes sense because we know that pulling her hands in is going to make her spin faster.